training. My name is Carl. In this training, we will explore the functionality of programmable logic devices, in particular, the architecture of an FPGA. To get started in our exploration of programmable logic devices, let's take a look at a typical system design. Here, we have a board with a number of chips, a CPU, I/O interfaces, flash, SDRAM memory, and a DSP chip. The circuit board required for this system is quite large in order to contain all of these chips. This increases the design cost and complexity. But what if we could contain the CPU, the I/O, and the DSP all in one chip? Well, that's exactly what programmable logic lets us do. An FPGA, or Field Programmable Gate Array, is a sophisticated and flexible piece of silicon that when used, a large amount of hardware can be removed from the system, reducing cost and power usage. At the same time, the FPGA can be used to implement custom hardware, allowing it to efficiently accelerate algorithms quickly, achieving performance gains otherwise not possible. You may not know it or realize it, but programmable logic is found just about everywhere, from your HDTV at home to the cell phone towers in your neighborhood to the ATMs at your bank. Digital logic in the form of programmable logic devices is there, doing everything from controlling how a system works, like a CPU, to behaving like a traffic cop in high-speed switching applications required for networking and communication. But what exactly is this technology? Where did it come from, and how can it be used in so many different applications? This training should help answer these questions, as well as how and why programmable logic technology is so desirable to digital logic designers. This training is a basic introduction to programmable logic devices focusing on field programmable gate arrays, or FPGAs. Software, such as, if you haven't already done so, I will highly recommend that you view the History of Digital Logic Design short online training available on the Intel FPGA training, the advent of the modern FPGA architecture, then moving on to design varies greatly with their CPLD predecessors. FPGAs varies greatly with their CPLD predecessors. FPGA labs are made up of a number of blocks of logic called logic elements, or LEs, and in more advanced devices, adaptive logic modules, or ALMs. Each of these logic blocks consists of lookup tables, registers, and other configurable features. Routing interconnect is separate from those logic blocks. LEs, or ALMs, may look similar to CPLD macro cells, but they are much more configurable and provide a number of extra features to improve performance and minimize wasted logic resources. The diagram here shows the detail of an LE in a typical FPGA lab. The LE is made up of three main parts: the lookup table, or LUT, the carry logic, and the output register logic. The LUT, or lookup table, is the key to the creation of sum of product functions out of combinatorial logic in an FPGA. The LUT replaces the product term array found in CPLDs. FPGAs uses 4 or more input LUTs to create complicated functions. A LUT is made up of a series of cascaded multiplexers where the LUT inputs are used as the select lines. The inputs to the multiplexers are programmed as high or low logic levels. The logic is called a lookup table because the output is selected by looking up the correct programmed level and routing it correctly through the multiplexers based on the LUT input signals. The program levels selected are based on the truth table for the function. As an example, this min term is routed through the LUT where A and B are high and C and D are low. This particular min term corresponds to this product term in the desired logic function. While it may seem like more logic levels are required to produce outputs on a LUT versus CPLD macro cell, the flexibility of function creation and LE chaining, which we'll look at in a moment, provide improved performance and help to minimize wasted resources. The synchronous part of an LE comes from the programmable register. It is usually driven by a global device clock, but any clock domain can drive any LE. Asynchronous control signals of the register, such as clear, reset, or preset, can be generated by other logic or come from an I/O pin. The output of the register can drive out of the LE to the device's routing channel, or be fed back into the LUT, similar to the feedback possible in a CPLD macro cell. The register can also be bypassed to produce a strictly combinatorial logic function. again similar to a CPLD. It's also possible to completely bypass the LUT to just use the register for memory or synchronization. This flexibility in the output stage of the LE makes it extremely useful for all types of logic operations. The final key section that distinguishes an LE from a macro cell is the carry and register chain logic. In the CPLD, carry bits and macro cell outputs can be fed into other macro cells, but this usually requires a return to the product term array. FPGA LEs contain specific carry logic and register chaining routes within labs to provide shortcuts for these signals. Carry bits can come from other LEs within the lab or from other labs in the device. Generated carry bits can be outputted to LEs or to the device interconnect. The LUT and carry logic can be bypassed completely within the lab to chain all the LE registers in the lab, turning them into a shift register, perfect for DSP type operations. The versatility of the carry logic and register chaining routes provides further performance and resource management gains over CPLDs. Because either the LUT or the register can be output to anywhere in the device, either in the same lab or through the device's routing channels, FPGA LEs can be configured to perform a function called register packing. With register packing, two separate functions can be output from a single LE, one from the LUT and carry chain logic, and the other from the output register. This can help save device resources, since a completely unrelated register function can be packed into an LE that's using only the combinatorial logic part of the block. With these building blocks in mind, let's take a closer look at how they are connected together to create an FPGA device. Here's a picture of some of the labs in modern FPGA device. This picture is from a tool called the Chip Planner inside Intel Quartus Prime software that makes it easy to see where logic is placed in an FPGA design. The darker color labs indicate that more of the resources contained within the lab are being used for this particular design. You can also see the routing channels running between the labs. To get more details on a particular architectural feature, you can zoom in on that feature, such as the lab highlighted here. Zooming on this particular lab, you can see that none of the logic resources are actually being used, indicated by the light blue background and the fact that all the resources in the lab are white. This lab and all the labs in this device contain many LEs, connected to each other and to the rows and column interconnect through the many visible small wires. You can zoom in further to look at individual LEs, such as this one. Here you can see it's made out of the lookup table and carry logic and the synchronous register logic. While the FPGA LE discussed so far has a definite design flexibility advantage over CPLD macro cells, LE cascading and feedback are still necessary to generate functions with more inputs than are available. To overcome this problem, all new FPGAs use a more versatile logic block as a replacement for the LE called an adaptive logic module, or ALM. An ALM is similar to an LE, but provides some key advantages. First, ALMs include 2 or 4 output registers to provide even more options for logic chaining, register packing, and generating multiple functions within a single logic block. ALMs also have the built-in hardware adder block. The adders in the ALM are dedicated resources that can perform standard arithmetic operations without having to generate those math functions in the LUT or in the DSP. This can improve math performance and simplify the LUT logic. The LUT in an ALM is the main differentiator from an LE. The LUT in an ALM is an adaptive LUT, or ALUT. An ALUT is similar to a LUT, but it can be split and configured into different sized LUTs to accommodate 2 separate functions of any type, from the very simple to the very complex. All 8 inputs can be used to perform complicated arithmetic functions, but the ALUT can be split in different ways for simpler functions, such as 2 LUTs with 3 and 5 inputs each. An ALUT can also be split to support a more complicated 7-input function with the extra input used for register packing. Splitting into 4-input LUTs makes the ALUT backwards compatible with 4-input LUT technology found in standard LEs. Finally, some other splits are possible if inputs can be shared between 2 functions. ALM-based FPGAs provide extremely high-performance logic operations using fewer resources and smart resources management. In a Field Programmable Gate Array, or FPGA, the labs are all arranged into a large array. and the device can be programmed and reprogrammed out in the field. Programmable routing is placed in the spaces between labs, similar to streets in a large city. This routing is organized as row or column in the interconnect. It may span the entire length or width of the device, or only a small segment, covering only a few labs in a row or column. Various device blocks, as well as other routing resources, can all drive into a given routing resource. This makes it very flexible for FPGAs to route various signals around the chip. The routing channels in FPGA devices seem simple, but they actually provide lots of functionality and connectivity. FPGA routing channels allow all device resources to communicate with all other resources anywhere on the chip. This was not always the case in some older non-FPGA devices. The Manhattan-type routing channels, along with different-sized fixed-length segments, make it easier to adjust routing to meet design timing requirements. As already mentioned, as the amount of available device resources grows, the number of routing channels only needs to increase linearly to continue to connect between all device resources. FPGA routing channels can be divided into two types: local interconnect and row and column interconnect. Local interconnect routes directly between LEs or ALMs within a single lab while providing shortcuts, often referred to as direct links, between adjacent labs. This is almost analogous to the programmable arrays found in CPLD labs. But FPGA local interconnect is separate from the lab logic it serves. The other types of interconnect is the row and column interconnect. This interconnect comes in fixed lengths and spans either a select number of labs or the entire length or width of the device. Lab I/O can connect to the local interconnect for high-speed local operation or directly to the row and column interconnect to transfer data to other parts of the chip. FPGA I/O control is contained in blocks found around the outer edge of the array and made available to all device resources through the FPGA routing channels. I/O blocks in FPGA devices are usually referred to as I/O elements. I/O elements contain most of the same basic features found in the older CPLD I/O control blocks, but they add many more features, making FPGA I/O elements extremely versatile for all types of designs. Besides basic input, output, and bidirectional signaling, I/O pins support a wide variety of I/O standards, including many of the latest low-voltage, high-speed standards. Pairs of I/O pins can be combined to support differential signaling I/O standards, such as LVDS. Other features include variable current drive strength and slew rate control to help improve board-level signal integrity. On-chip termination in the form of pull-up resistors can be enabled to help reduce termination component usage on the board. Some devices include clamping diodes and I/O elements that can be enabled when used as I/O for PCI bus. Any unused I/O pins on the device can be set to open drain or tri-stated depending on the needs of the design. These are just examples of the capabilities of a typical I/O element. Some devices may provide even more features. Here is what the basic logic of a typical I/O element looks like. Not shown in this diagram is all the other hardware used to control many of the aforementioned features of the I/O element. The I/O element is divided into three major sections. The input path captures incoming data on input pins in an input register or connects the input directly to logic in the device through the routing channels. The output path contains output registers for synchronizing logic or for memory usage, similar to the output register found in CPLD macro cells. Since registers are found in both the main lab logic as well as in the I/O element, either can be used, freeing up registers in logic for other use. Of course, the register in the I/O element can be bypassed if desired. The final section of the I/O element is the output enable logic. This logic controls the output enable buffer. This section may be used if the I/O has been configured as bidirectional pin or to synchronize output data with other outputs on the device. Modern FPGA devices contain specialized hardware blocks in addition to labs. These dedicated resource blocks take up one or more blocks in the array and are completely accessible through the FPGA routing channels. Often these specialized resources are arranged in a particular row or column of the blocks in the device. Memory blocks are dedicated blocks that can be configured into different types of memory devices. FPGA memory blocks can be constructed into single or dual port RAM or programmed ROMs. They can also be used as shift registers or FIFO buffers in place of lab logic. Since FPGA memory blocks are programmed just like other structures in the device, they can be initialized with any memory content desired at power-up. This is extremely useful for this design debugging since any memory pattern can be initialized and tested. Some devices include memory labs or MLabs. An MLab can be used as standard lab, but it can also be configured as a simple dual-port SRAM. The capacity of an MLab is much smaller than a dedicated memory block, but has a wide and shallow memory. It can implement the shifting and FIFO operations required for DSP applications without wasting a high-capacity memory block resource. The other type of dedicated resource block typically found in modern FPGA devices is called a DSP block. The DSP block contains embedded multipliers and adders to perform arithmetic and multiply-accumulate operations. They can be used instead of ALM logic to improve arithmetic performance in a design. A portion of a block diagram for a DSP block is shown on this particular slide. Some devices also feature high-speed transceivers. These I/O structures support high-speed protocols with transfer rates in the gigabit per second or higher range. These high transfer rates are typically used for communication networking devices. Altera devices support dozens of I/O standards used in a variety of different applications. Different FPGA devices contain different amounts of these type of specialized resources. The device handbook should always be consulted to determine if a particular device provides enough resources for a given design. Since FPGAs are based on synchronized register logic, clocking and clock control structures are an important part of an FPGA architecture. Clocks are basically high fan-out control signals, so FPGA devices include hardware to control where the clock signals should go and how the clock signals get to their destination. All FPGA devices include dedicated clock input pins. These pins take in a clock signal and connect it directly to other clock control structures on the chip. Other pins can be used as clock pins, but the signal may need to go through other logic structures. When not used for clocking, clock input pins can be used as standard I/O. Clock input pins typically feed into phase lock loops, or PLLs, on the device. PLLs can generate other clock domains based on the characteristics of the input clock and ensure that all clock domains are in phase with each other with minimal skew. We'll look at PLLs in more detail in a moment. Advanced FPGAs also include delay lock loops, or DLLs. DLLs are useful for adjusting and locking the phase of a clock quickly. They are mostly used along with PLLs when creating an external memory interface, such as one that controls external DDR3 SDRAM memory. The DLL dynamically adjusts the phase of a strobe signal to align it correctly with the data being read and clocked by the strobe. The addition of a DLL into such a design provides much more accurate tracking when changes in voltage and temperatures are detected, allowing for some devices to achieve much greater memory interface speeds. Clock control blocks are basically clock control traffic cobs. They are used to select which available clock should feed the device's clock routing network. They are also used to enable or disable selected clocks during power up or power down. The ability to enable or disable selected clock is also a device power saving technique. Any logic normally clocked by a clock that gets disabled is essentially shut down, saving overall dynamic power. The clock routing network consists of a routing channel used to fan out clocks to all the logic in the device. These are special routing channels that are usually separate from regular row and column interconnects. The global network of clock interconnect may connect to all logic, but some devices contain regional or hierarchical clock networks that feed only certain parts of the device. For example, a clock network may feed only a single quadrant of the device. In this way, a clock used for a particular region or part of the device does not use up the global clock routing network, saving clock resources. As mentioned, PLLs are structures that can generate different clock domains and ensure minimal skew between the generated output clocks. PLLs are programmable, allowing the designer to easily create multiple clock domains at various frequencies, duty cycles, or phase shifts for use throughout the design. As an example, here a simple PLL design with one input clock and 3 output clock domains based on the input clock. The input coming from a clock pin is 100 MHz. The PLL output clocks are a 100 MHz clock that's identical to the input, a 200 MHz clock, and a 200 MHz clock with a 90-degree phase shift with respect to the input. These clocks can be fed into a clock control block for distribution throughout the device clock network. PLLs are usually programmed at power up, but can also usually be reprogrammed on the fly during normal operation. With all these different types of architectural structures in an FPGA to configure and control, a lot more programming information is required. Also, to support possible connections between everything while still including a large amount of available user logic, simpler and smaller programming structures are needed. To meet these goals, FPGAs use SRAM cells to program logic levels and make routing connections. To see how FPGA programming works with SRAM cell, on the left is a typical interconnect junction between a row and a column. The interconnect includes switching transistors on all possible connections between the vertical and horizontal routing. The select gate control on each transistor comes from an SRAM cell. A typical SRAM cell is shown on the right. An SRAM cell is basically a latch. When programming is enabled, the programming bit is latched into the cell. The output of the cell is the complement of the programming bit. So to make a routing connection, the programming bit is 0, putting a 1 on the gate of the programming interconnect transistor, closing the switch and making the connection. Obviously, this type of programming architecture requires more transistors than a CPLD programming array. However, all the transistors are standard. No flowing gate transistors required, so no special fabrication is required. The main problem with this programmable architecture is not the number of transistors required, but the fact that it is volatile. Whenever powered off, the latch is cleared. This means that FPGA devices must always be programmed at power on to configure the device SRAM cells. If all of the programming hardware on the FPGA is SRAM based, the programming information must be stored somewhere else that is non-volatile so that the device can be configured at power up. Typically, an external device such as EEPROM, a CPU, or even a CPLD is used to perform FPGA device programming. With most FPGA devices, there are two ways the programming can occur. With active programming, the FPGA automatically starts communicating with the external device on power up and basically programs itself. With passive programming, an external device, usually a CPU, controls how and when the FPGA gets programmed using data stored in an EEPROM or other configuration device. Either way, the same programming process will need to occur whenever the FPGA is reset or power cycled. As with CPLD devices, FPGAs have a JTAG interface for programming in a lab from a PC. However, for production, one of other programming methods must be used to configure the FPGA at power on. This slide illustrates the organization of a typical FPGA chip. This device includes programmable I/O, programmable core logic, programmable memories, and programmable DSP blocks. DSP blocks perform digital signal processing functions with high-speed multipliers and adder logic. The inset shows an expanded view of the serial transceiver block that is used in many common high-speed I/O standards. External to the FPGA is a configuration device, which is usually a flash memory that contains the settings for all of the programmable functions within the FPGA part. With the features described, it's easy to see how FPGAs provide many advantages to the system designer. They include a lot of user logic in a high-density package to enable the creation of all kinds of logic functions, from the simple to the very complex. FPGAs are high-performance devices. Older programmable logic devices were not often used as replacements for ASICs or dedicated logic chips because they could not achieve the clock speeds of those dedicated devices. However, modern FPGAs provide the performance needed for many high-speed applications, making them an affordable solution for many different types of system designs. FPGAs include different types of dedicated hardware, such as memory or DSP blocks, that makes it easy to combine different functions into a single design. FPGA I/O is extremely flexible, with many supported I/O standards and features that can be customized for specific applications. Finally, with their SRAM programmable cells, FPGAs can be programmed very quickly, making the disadvantage of required programming at power-up almost a non-issue. Intel offers a number of different FPGA device families. The Intel Cyclone devices are low-cost, high-performance devices with a large amount of logic suitable for most mid- to low-end applications. Newer Intel Cyclone devices even include high-speed transceivers, a hardware feature usually only found in higher-end devices. In the mid-range, Intel Aria devices are the lowest-cost devices that include high-speed transceivers operating at high-performance levels than Intel Cyclone transceivers. Intel Stratix devices are high-performance, high-end devices featuring increased logic density, high-speed transceivers, and the ability to create complete systems on a chip. As we've said earlier, SRAM-based FPGAs are volatile in that every time the board powers up, the FPGA needs to be configured from an external source. Intel's Max families are non-volatile FPGAs. They are still SRAM-based FPGAs. However, they all contain an internal flash on the same die. The internal flash contains both a user flash memory and a configuration flash memory. At power up, the configuration flash memory containing configuration data will be used to load the configuration RAM of the FPGA. The non-volatile FPGA families have characteristics similar to traditional CPLDs in that they are instant on, so it can be used as the first device on the board to control bringing up of other components, and they are also low cost. Some variants of Max10 families even include integrated ADCs with temperature sensors to provide lower latency and flexible sample sequencing. Newer generation FPGAs may contain an embedded ARM processor and its surrounding subsystem. Here's a more detailed blockgram of a 28nm SoC FPGA. The portion in blue is the hard processor system, or HPS, and it contains a multi-core processor, for example, the Cortex-A9 NP core processor. The processors share a 512 kilobyte level 2 cache and has a rich set of peripherals, including triple-speed Ethernet, USB on-the-go ports, interfaces to flash memory, general-purpose embedded peripherals such as UART, SPI, CAN, and I2C, and a shared multi-port SDRAM controller that supports most modern DDR standards. Two high-speed interfaces connect the HPS and FPGA fabric, with a third interface dedicated to low-latency traffic from the processor to the FPGA. The processor has direct access to the FPGA configuration controller, so it can configure the FPGA under program control. The deep blue portion represents the FPGA fabric, and the gray blocks represent additional hard IP functions available to your custom logic, including additional multi-port SDRAM controllers, PCI Express ports, and high-speed serial transceivers. The HPS and FPGA have their own dedicated I/O and can share some I/O functions when necessary. To finish up this training, let's take a look at the general design methodology used for creating an FPGA design and how the Intel Quartus software implements this methodology on a device. The FPGA design methodology can be summarized with a simple design flow. Based off the original design specification, the design is created typically with some form of graphical tool or coded in a hardware description language that describes the behavior or logic structure of the design at the register transfer level, or RTL. This is usually followed by RTL functional simulation using a tool such as Mentor Graphics Model Sim or other third-party simulation tools. Note that a simulation at this point tests logic functionality only. Timing delays in the device are not taken into account. Next, the design must be synthesized to translate it into logic primitives specific to the selected target device. During the synthesis process, the design can be optimized to meet specified size, performance, and timing constraints. You can perform synthesis in the Quartus software or use a third-party synthesis tool such as Mentor Graphics Precision Synthesis or Synopsys Simplify. The result of synthesis is a database of information referred to as the post-synthesis netlist. No matter what tool is used for synthesis, the Intel Quartus software must then be used to perform the place and routing of the design and the target device, often referred to as fitting. The Quartus Prime software fitter maps the synthesized logic primitive selected in the post-synthesis netlist to specific logic structures in the target device and creates routes connecting the logic together using the device's available interconnect. The fitter uses specified area, performance, timing, and power constraints to guide the process. The result of this is a separate database called a post-fit netlist. The netlist generated by the fitting process is also used to perform a number of tasks. It's used to perform static timing analysis in a tool such as the Timing Analyzer built into the Quartus software to verify that timing and performance constraints are met by the fit design. Usually the combination of functional simulation and static timing analysis is enough to verify the design. In preparation for placing the device on the circuit board, you can use IBIS and HSPICE models generated by the Intel Quartus software or provided by Intel to perform board-level simulations. Finally, the post-fit netlist is used to generate programming files for configuring the SRAM cells of the target device on the printed circuit board. After programming and configuring the device, a number of on-chip debugging tools, such as SignalTap Embedded Logic Analyzer, also included with the Intel Quartus Prime software, can be used to verify that the design works correctly on board. Most FPGA designs are described in either the Verilog or VHDL hardware description languages. Intel's Quartus software synthesizes the design, which means translating the hardware description language into hardware, and then it runs place and route, or in FPGA terminology, fitting, and finally assembles a programming image to download into the FPGA. Intel's Quartus Prime software is a fully integrated development tool that completely supports the design methodology described in the previous slides. It provides the usability and flexibility to create, optimize, and verify an FPGA or CPLD design from start to finish entirely in the Intel Quartus Prime software environment without the need to purchase any other tools. The software provides a number of different ways to create a design and include advanced synthesis and place and route engines to implement the design in a device. The software includes a special edition of ModelSim called the ModelSim Intel FPGA Edition to perform simulation. It also includes tools to perform a static time analysis, estimate device power usage, and programming of the device. As you've already seen, other features of the software, such as the chip planner, allow you to get detailed information about how a design is mapped to hardware in a target device. While traditionally writing low-level HDL is the only way to utilize the features of an FPGA, there are now many ways to generate HDL for FPGAs using high-level tools. Here are some that are offered by Intel. The Platform Designer System Integration tool is a GUI interface that allows users to quickly integrate IP functions and subsystems together and generate the HDL representing the system, including the automatically building the system interconnect using standard memory mapped or streaming interfaces. The Intel FPGA SDK for OpenCL allows users to compile C-based OpenCL code into an operational FPGA bit stream. The Intel HOS compiler compiles C-based code into an RTL code, which you can integrate using the Platform Designer or RTL. And finally, our DSP Builder design tool is a block set inside MATLAB Simulink environment, which then can be used to automatically generate HDL directly from the Simulink modeling environment. To learn more about Intel's award-winning Intel Quartus design software, use the references here. You can also download the free version of Intel Quartus Prime design software on the Intel FPGA website. There are a number of follow-on free online trainings that talk about how to get started with the Quartus Prime software. Depending on your time budget, please view these online trainings to see how easy it is to get started creating FPGA designs. Lastly, we also offer a full-day instructor-led training which covers detailed information about Intel Quartus software, including lab exercises. This entire class is also available for free in online format. To sum things up, programmable logic devices came about originally to reduce component usage on cramped circuit boards, saving cost in the process. With performance increases and features unique to programmable logic, FPGA devices have become low-cost alternatives to dedicated ASICs. Finally, PLD design software, such as the Intel Quartus Prime software, makes it easy to create, test, and implement all types of designs, from simple combinatorial logic to complicated system-on-chip designs using programmable logic devices. The fastest way to get started with FPGA development is first to target a development kit. Intel and its partners offer many boards for each device family that have the features you're looking for. Follow the Intel FPGA Development Kit landing page linked here to see all of the available boards. I've also listed here many popular low-cost boards. These cost as little as $50 and have some advanced features such as touch screens and cameras. Please look for these boards as well as corresponding reference designs to get started. Here are some resources you can go for more information about FPGA devices. Be sure to check out the device handbook for each of Intel's programmable logic device families found on the literature page of the Intel FPGA website. You can find articles about FPGA devices on the web and can take a look at some books that provide a wealth of information about the history of programmable logic and how current devices operate. I've also included links to articles on the history of programmable logic technology from Intel's FPGA Design Journal. It's divided into 3 parts. In the beginning, from glue logic to subsystems, and the third decade, the FPGA as SoC. This concludes the training. But one last thing, when you register for this online training, you should have received a link to a short survey where you can provide feedback. We'd greatly appreciate it if you fill out that survey right now. We're constantly updating and improving our training